Good morning, everyone. Welcome to our first lecture on magnonics. And today, actually, our task is to refresh our memories about magnetism. So we will just go through the very basics in the solid state physics and magnetism, that we understand why some materials are magnetic, so why not? Because the main point for a spin wave is that we need good magnetic material in which it can propagate. So today we will cover atomic origin of magnetism after basic introduction, why some materials are diamagnets, some are paramagnets, what are the ferromagnets, antiferromagnets, and we will finish with magnetism in metals and alloys, where we need to use different model to describe everything. For people in YouTube, there is already a similar, more detailed lecture uploaded. Advanced materials, where more or less the same slides you will find is more detailed information. Here we just use a minimum which is needed for us in order to understand the following material. So I would like to start with the history of magnetism, not because I'm a big fan of history, of course I like history as everybody, but here my motivation is to show you the evolution, and you will have a chance kind of to put yourself in the position of a researcher. Then you will understand material much better. So where did we hear about magnetism for the first time? So people believe that this was in China, 3,000 years before Christ, and archaeologists have found the spoon, which they believe is a compass. Of course, one can wonder that it's very heavy, big, and probably it would not rotate if you just place it on a table like it's shown here. But we never know what was in reality, so it was quite some time ago. Maybe they placed it on water, maybe they used some vibrations, but more or less, at least partially, people believe that this was really a compass. But then we are coming to Greece, 800 years before Christ, and people have found magnetite, and they have found that in this strange stone, they attract each other, and they gave name magnetite, and principally, that's where word magnetism comes from. Maybe also magic, I don't know. It's still an open question for me. Then we have a long step in history, and people have realized that this magnetite or magnet, there are some magnetic field lines, as you know, and there are poles, yeah? And that if you put two magnets with identical poles, they will be repulsing. And if they are opposite poles, they attract each other. And then there was Middle Ages, so again some poles. But afterwards we come to John Michael, who in 18th century has shown that if you will cut this magnet in the middle, you won't be able to separate South and North Pole. Instead, you will get again two magnets. So there are no magnetic monopoles. Then we are coming already more or less to our physics. Ampere, they have shown that if you will have, he has shown that if you have two current carrying wires, they attract each other. Then Ørsted has found that if you will send current through a wire, it will create a field, and you can feel it with compass needle. There is an interesting story behind. They say that he discovered it during his lecture, that he was showing some experiment with electricity, and there was accidentally compass laying on the desk, and students has noticed that it turns. Although Ørsted said that it was his plan, we don't know what was in reality. It was quite some time ago, but anyways, there is a fantastic phenomenon which is used now every day in every life. So then Faraday said that electric current can be generated by moving magnets with the opposite effect, as you know, and then Maxwell more or less placed all this together. And this is core of classical physics. So where do we use magnetism in our everyday life? And it's, I suppose, it's everywhere. So navigation, our Earth has some liquid conducting material rotating and creates a field around, and a compass fills this field. There are many nice stories about birds, that birds also kind of see this field. They made very fun experiment, place such little magnets on neck of birds, and they really start flying in random directions. So they, and then I think latest research is that there is really kind of magnetic protein or something in the brain or in eye, that they really more or less see these lines. Credit card, of course, we have this information we carry on stored on magnetic media. Not a lot of information, but it's about money. And don't put your card on big magnet; it will be demagnetized. Hard disk. So nowadays we are using in our smart laptops, it's usually SSD flash drive, which is semiconductor. It's not magnetic, and it's faster, and it's kind of it's really fantastic technology. But if you store data on a cloud, then most likely these servers are using hard disk still, because it's cheaper and because you can keep information for longer time there. So hard disk are intensively used. Generators, motors. So some motors in Tesla at one of the axis, at least, they use, to my knowledge, electromotor with permanent magnets in there, and you need these permanent magnets. Data storage, so this is so-called MRAM. It's a new technology which is already on market, but for some particular purposes. Sensors, many magnetic materials and spintronics phenomena, magnetics used in sensors, and we have many sensors everywhere, especially in the view of robots are coming and so on. It's very important. We have this nice train, levitating train between Shanghai, I think, and Shanghai airport, and it's levitating. You need magnets here, and of course magnets are intensively used in medicine, so for MRI, and in science, particle accelerators, mass spectrometry, and so on. So principally magnetism is everywhere, and it's a very nice field. And which material I use to explain you is mainly this book of Kannan Krishnan. Like it very much. Our library bought it in electronic form. You can download it, and it's on fundamentals and applications of magnetic materials. But the first chapters also give you very good basics of magnetism, especially. It's written in a style of, I would say, good to read for experimentals. You understand it's very well. And I'm ready to go to atomic origin of magnetism. Other questions to the very back introduction? I would like to start with a periodic table of elements taken from Krishnan. So you all know it very well. But here, in addition, you have a color code. And white, this P means paramagnet. Green, D means diamagnet. F means red, means ferromagnet, and gray, F, antiferromagnet. So there are different types of materials in terms of their response to the applied magnetic field. And you see that majority of materials are paramagnets. There are many diamagnets, and only some are really magnetic or antiferromagnetic. You see also here numbers. Numbers in yellow, it's Curie temperature. So this material is getting ferromagnetic for temperature smaller than this value. If you go to higher temperatures, it becomes paramagnet. And the same for antiferromagnets, but it's named Néel temperature. It's shown here. You see, majority of the cases, this is low temperature, below 270 Kelvin. And this is a temperature below which antiferromagnet is actually antiferromagnet. And our job, more or less, to understand why some materials are ferromagnetic, some diamagnetic, and so on. Again, I would like to start with a Bohr model of atom, where we have negatively charged electron flying around positively charged nucleus, which is located here. And if you will look on it in the terms of current loop, you will see that this current which is created by this electron motion can be found simply by charge of electrons. We consider only one divided by t. T is a periodicity. So it's simply amount of charge transferred per unit of time. Or you can rewrite it in terms of circular frequency omega charge, and here you will have 2 pi. So charge of electron is known, it's constant. Radius, we can take 5×10 to the power minus 11 meter, and this is Bohr radius, and period is very, very short, 10 to the power minus 16 seconds. As a result, if you will plug this atomic scale, yeah, everything is very small, but if you will plug these numbers into this formula, you will get current of order of milliamp, which is very macroscopic, very serious current. And it might be surprising, but the reason is very simple, because of this T. Yeah, so the electron is flying very large, very fast. And if it's the case, then what we have, it will create also visible, let's say, pronounced magnetic moment, because as we all know, if there is a loop with a current, there will be magnetic moment pointing perpendicular to it, and it depends on the current in this loop and on A, it's a surface. So here I consider it to be simply perpendicular, so all vectors are removed, it's color variable, but you can calculate what is the size of this, magnetic moment can be defined, and you see that it depends on omega, circular frequency, and radius, and charge of electron. Minus means that it's negatively charged. So minus here is because electron is negatively charged. So E is positive. Good. So there is electron, it creates magnetic moment shown here with red line. Electron is light particle, but it still has a mass, and if it has a mass, then there is also an angular momentum, LE, and this is a formula which we know from mechanics. You can find it simply as mv, so linear momentum times coordinate vector r, or you can rewrite it in terms of omega. And since mass is positive yet charge is negative, L is pointing in the opposite direction with respect to the mu. So they are anti-parallel. Now what you can do, you can make a very simple mathematical trick. You see that in both formulas you have omega r square. You just take it from this formula, and you take omega r square from this formula, compare one to another, and then in such a way you can get a coupling between magnetic moment and or angular momentum L, and you see that they are coupled by fundamental constants only. So this is named gyromagnetic ratio gamma, which we will use later. But here it's in general form. So this is charge of electron, mass of electron is in here. Yeah, so that's what we have. And you know all Einstein-de Haas experiment, when they have shown there was big cylinder magnetized, and they applied current to a loop in order to magnetize cylinder in one direction or into the opposite direction. This cylinder started to rotate, and this is a direct proof that magnetic moment and angular momentum are really coupled, because this angular momentum from the atomic scale at the end of the day, it comes to the macroscopic angular momentum of the body. If you are, so here it was all quasi-classical, except that the Bohr model of atom works only in quantum regime when this electron is rotating here stably. And but if you will go now to quantum physics, of course everything is quantized, energy first of all, but also it brings us at the end of the day to the quantization of magnetic moment, mu L plus L. So here quantum number L, it's orbital one, and we have mass of electron, charge of electron. Or you can rewrite it in terms of this mu B, where mu B is the smallest magnetic moment associated with electron. It's called Bohr magneton, and here H is Planck constant. So all well known, and now we are making next step. As I said in this promo lecture on magnonics, we need to take into account also spin of electron. So spin of electron, purely classical business, but you can understand it also as orbital, also as angular momentum. So it's mechanics, it's not magnetism. But it looks like, for example, if your electron would rotate. It's very unphysical, but easier to understand. And like we made analogy, yes, so this is motion of Earth around the Sun. And this is a rotation of Earth on its own, when we have days and nights. And the origin of this effect lies in the quantum mechanics within a relativistic framework. So principally in my slides, I use especially a lot of text that people can work with them afterwards. In video, it's always possible to put on pause, and I just present the main issues. Of course, we also have to quantize spin, and magnetic moment associated with spin is equal mu s, and it's equal, here you see this G factor Gs, is named spectroscopic splitting factor, and it's a order of 2 for spin, and for orbital momentum it's around 1. So there is a difference in magnetic moment from spin and from orbital motion. And here's written this another analogy how you can understand spin. Spin is not a current loop, but for all practical purposes, it behaves like one. It means that we can look on spin as on a little loop, like this black line shown here. Yeah, and then it helps us to understand, although it's of course just a model for us to understand this better. What's also important, of course, if you will put electron in the applied magnetic field B or induction B, then there will be a torque equal ms cross product B. Good. So much about spin. Spin was discovered in Stern-Gerlach experiment. Please check, very interesting experiment. Again, as usually happens, people were searching for the quantization of orbital momentum, but then they have found something strange. And at the end of the day, it was discovery of spin. In this lecture course, we will use the following physical values. If you are talking about single electron, magnetic moment associated with this will be given as mu, and we measure it in ampere meter square in SI units system. If you are talking about magnetic moment of atom, I will use m. That's all taken from Krishna, and I think it's a good way. But in majority of the cases, we are going to speak about m large. And m large, it's a magnetization. So it's a kind of density of magnetic moments. So you need to take average of all magnetic moments, normalize it with volume, and magnetization is measured in ampere divided by m. Yeah, so it's slightly different. So do different units compared to mu and m. Very important parameter, which today we are going to use intensively, is susceptibility high. Susceptibility has no unit, but it's you can find it as m over h, and physical meaning is very simple. It describes you how your body reacts to the applied field. So if you have material, you apply magnetic field, and there will be created magnetization, then chi is not 0. Then it means that it's feels magnetic and reacts to magnetic applied field. If you apply magnetic field and nothing changes, then chi is equal 0. Yeah, so then it's 0. And in the first case, it was non-zero. This table from Krishnan, very important table, and it also shows us two different system of units, CGS, centimeter gram second, and SI universal system. Of course, nowadays we are trying to use SI as much as possible, and in lectures, especially in education. But if you will go to literature till now, especially in magnetism, people pretty often use CGS system, or they use both systems in the same paper. That also happens. And let us briefly go, because these parameters we need to use through the whole lecture. Magnetic field H, Oersted in CGS, ampere per meter in SI, magnetic inductance B, Gauss in CGS, Tesla in SI. Then important magnetization in CGS is mu per centimeter cubic, in SI it's ampere per meter. And also important this ratio between M, H, and B. By the way, in my lecture, I pretty often will use word magnetic field H and magnetic field B. Don't be confused, because strictly speaking, it's magnetic inductance, but all this terminology varies a bit from book to book, from country to country. Therefore, it's important, let's say, H and B, that you understand what I mean. And this ratio which couples B, H, and M is very important, and here you see how it looks like in SI system. So B is equal mu0 H plus M, and physical meaning is easy. H you can apply in vacuum. So if you have no materials, field which you create, it's H. But if you have some material, your material can give additional field. Let's put it like this in the simplest word, associated with this magnetization M. And then B is this field inductance, or field B is more or less sum of two fields together. And you see that here staying also this fundamental constant mu0 permeability of vacuum, which has no physical meaning, but it has, it's important that you have everything's right with units and you can work with SI units of system. If you do the same in CGS, then B equal H plus 4pm, looks slightly different. And why people like CGS, they believe that it's kind of more physical, because if you take vacuum, where magnetization is equal 0, then field B is equal to field H, as it should be. Of course, in order not to mix up, since people introduced that field is measured in Oersted and inductance B in Gauss, but one Oersted is equal to one Gauss. That's kind of how people went around. If you do the same in SI, then B is equal mu0 H. Yeah, and it's not clear why, if there is vacuum, there is no magnetization, why I have different values. But this was needed in order to put all these units together. Here also you have susceptibility H, so you can rewrite this formula in terms of chi, or you can rewrite it in terms of mu, which is a permeability. Good, so much. This is for you just to check with which parameters we work, what are the key formulas. So these are important. Torque is important in SI. It's found as M cross product B. In CGS, it's M cross product H0. And of course, potential energy, again, slightly different. In CGS, it's M times H in scalar product with minus, and for SI, it's M cross product B. Questions? No. Okay. And now we are coming to diamagnets and paramagnets. So let us try to understand why some materials diamagnets, some are paramagnets. But before, let us have a look on the classification. And this classification is taken from the book Stancil Prabhakar. This is one of two commonly used books on spin waves. And they use this nice block scheme to classify materials, like you do in programming. So first question you need to ask, if there is permanent magnetic moments in your system. And if you say there are no permanent magnetic moment, it's diamagnetism. Second question, you do have magnetic moments. Then question, if there is a long range order, it means that they are filling each other. If no, if there is a cause, they all pointing in different directions, then it's paramagnetism. If they are sorted, then it can be either ferromagnetism if they are parallel, or you go to anti-parallel case, and then you can have two cases. If they are equal, it's our antiferromagnet, which we have seen in the table of elements. And if they are unequal, then we have so-called ferrimagnetism. Yeah, so one letter is different. Ferrimagnetism, ferromagnetism, completely different meaning. Also, ferrimagnets usually behave like ferromagnets. And another way of classification as shown here, it's again from Krishnan, and it's based on the susceptibility. So antiferromagnet, for example, when you apply some field, there will be reaction. So one sublattice will react to the field, but another sublattice also will react in the same way, but with the opposite sign. So it means that reaction of your material to the applied field will be compensated. And antiferromagnet, also it's as ferromagnetic as ferromagnet, as magnetic as ferromagnet, unless you apply very large field, the response will be zero. Then susceptibility is zero, and it looks like there is no magnetic response. Therefore, antiferromagnets were discovered not so long time ago, compared to others. Now, if you will work with diamagnets, you see that it has non-zero but still very small susceptibility, 10 to the power minus 4, and it's negative. So which means that when you apply magnetic field, it creates this magnetization will be pointing in the direction opposite to the applied magnetic field. It's negative. And if you will go to superconductor, some of you might know that it has two main properties. First of all, it's practically zero resistance, but also it has it repels applied magnetic field. What does it mean that it repels applied magnetic field? It means that when it will create field equal to the applied one, but with the opposite direction. Therefore, M is equal minus H, and as a result, superconductor is ideal diamagnet. Therefore, it's minus 1. If you go now to the right side, you see that here we have paramagnets. They have positive susceptibility. So it means that high is positive, M, which is created by the applied field, H pointing in the same direction. Still small, but larger, like 100 times larger than susceptibility for diamagnets. And then we have values which are even larger than 1. And these are our ferromagnets, what we usually get used to name as magnets. That's what we all have when we play with whiteboard, with magnets, which we stick to the whiteboard. So you see this larger than 1, so it means that your material can create magnetic field on its own. So much about systematics and classification of materials. And let us try to understand what is diamagnets. So you see, usually people say that diamagnets are non-magnetic. This is strictly speaking not correct. They are magnetic, otherwise their susceptibility would be 0. But they are very weakly magnetic. And our question is that first of all, they are weakly magnetic, and second, their magnetic response appears only after you applied magnetic field. So if there is no magnetic field, it's really non-magnetic. But as soon as you put magnetic field to diamagnet, it creates a magnetic moment. Why it happens? Since now we are discussing so-called Langevin theory, and here's written, yes, the diamagnetic susceptibility is very small, negative, and so on. But what we need again our Bohr model of atom. For example, this dashed line. Now it's just not vertical, but it's plotted like that. And if you have this dashed line, there is a magnetic moment pointing like this dashed line here. It's some moment of time. So you have mu orbital, like we have seen already, which is given through omega r square, or you can rewrite it in orbital angular momentum. Now, if you take this magnetic moment and place it in the magnetic field H, which creates induction B, yeah? Then there will be torque, like we have seen in that table on the previous slide. And this torque is equal to dl over dt, change in the angular momentum, mu orbital cross product B. And then you will get such formula where it's staying omega L, which is just rewritten this part, which depends on the mu0 E mass of electron and applied field. And this is named Larmor precession. So physically what happens that when you have this magnetic moment and you apply magnetic field B, it starts to precess. Larmor precession, which we know very well. And after half period of precession, you will have mu L pointing along this line. And it precesses like it's shown here. Next step is very easy, because as long as it precesses, you can draw, imagine that you have an electron, yeah, it's always moving here very fast. But imagine that you have fixed electron here on top of this loop. Then what happens, this electron will be rotating like this, yeah? Like it's shown in this dashed line. And what does it mean? It means that your Larmor precession creates a new current loop. And it means that we have new current loop, which creates a new magnetic moment, mu precession, shown here. So it means that on top of the mu L, we will get mu Larmor, shown here. And this one can be found. So if you want to go step by step, how this formula is derived, it's all done in Krishnan. Here I give you just the final result, that magnetic moment of this precession will be defined by the applied magnetic field H. Yeah, so it all depends on the Larmor precession. And here R squared, it's now coordinate vector, but averaged, yeah, because electron is moving over all these coordinates, so you need to take into account averaged coordinate vector. But the most important for us is that you see the direction of mu is positive, pointing in the direction opposite to the applied field B. So it means that in diamagnet, when we apply magnetic field, before we apply magnetic field, nothing happens. When we apply magnetic field, we will get Larmor precession, which will generate magnetic moment, trying to compensate our applied magnetic field B. Then what you can do, you can calculate diamagnetic susceptibility. You just take magnetization, which is more or less averaged this magnetic moment over the volume, so normalized by the volume, and you divide it by field H, more or less this field H, and then you are coming to this value where you need to take into account R squared. It's now different R squared. It's now not only averaged R squared for one electron, but for all electrons in the orbital. So here we are considering already atom, and that is atomic number, so we consider many different orbitals, and R squared takes into account average coordinate vector for all of them. So we have here Avogadro number, we have density rho, and atomic weight E. But that's how you can see the susceptibility of a diamagnetic material. Let us have a look which materials are actually diamagnetic. Some metals, bismuth, beryllium, silver, gold, semiconductors, germanium, silicon, copper is diamagnetic, gallium arsenide is semiconductor is diamagnetic. And here you see the susceptibility with a factor 10 to the power -6. It's very weakly magnetic. Helium, argon. So all these noble gases, molecules, H2N2, yeah, hydrogen, nitrogen, up diamagnetic. And then what is very fun, water, blood, principally majority of organic compounds are diamagnetic. So it means that we are diamagnetic. One nice example of ideal diamagnetism, high equal 1, is levitating superconductor. So we always happy to show this demonstrator to kids, to show that physics is very interesting. And why it's levitating, the story is very simple. You remember this formula, the potential energy of magnetization M placed in magnetic field B, induction B, is equal minus M scalar product B. And now for diamagnet, they are antiparallel. So it means that your energy is proportional to MB. It means that the larger B, the closer your diamagnet to the magnetic field, because magnetic field is larger at the surface and then it decreases. The closer you are to the magnetic material, the larger is your potential energy. And as we know, every physical system is searching for a way to minimize potential energy. And as a result, we can get a situation that diamagnet, this force which is pushing it away from the surface from magnetic field, trying to move it in the direction of smaller field, is compensated by mg, which is trying to go down. Therefore, you can get some, I think this is graphite, little very light particles. They can levitate without superconductivity, but you can usually we are demonstrating superconductor because they are very strong diamagnets. Or you can rewrite the same what I just told you in terms of force, but here you need gradient of field, dB over dx, but also it will be pointing the direction up. So levitating trains are also working on this principle, and at least one of them is functioning in China. Little detour as a break. You know that there is Nobel Prize. Yeah, Todd Zeilinger got one recently here at the faculty. So a great pleasure to see his PhD student in the room. And but there is Ig Nobel Prize. And this is something opposite. It's like a joke, kidding Nobel. So it's like a joke. People give it every year, and the motivation, I find motivation very cool. Honor achievements that first make people to laugh and then make them to think. So we need to think to laugh in order to think. That's the idea. And very nice example, Andrii Chumak, who actually got Ig Nobel Prize in 2000 for levitating frog, but 10 years later he got Nobel Prize for graphene, and which also is very intensively studied here at this faculty. And let me just show you this video about the levitating frog. It shows that we are ferromagnetic, yeah? That we are diamagnetic, sorry. I will try to make some sound. So if here you need strong magnetic field, it means you need superconductor. And superconductor, you need a low temperature. Like it's shown here, using this dual in order to cool down the system, in order to achieve big magnetic field. They have this fantastic, of course they use this research not for levitating, this cryostat not for levitating frog, but for physics, but they decided to do this experiment, and you see that frog is levitating. That's for what they got the Nobel Prize. It's a very small frog, if I understood it from this video. It's alive, it's all fine. Probably it's a bit surprised what is going on. So if you would find, or any other, some insects, if you will find a big enough magnet, then we also can jump in and we also will levitate, like it was shown in that picture. Okay, so much fun. And I'm ready to switch to paramagnets. Question, was the idea of diamagnetism clear? Or there are some questions? Oh, so good. Then we can, yes?
Have humans been levitated with magnets yet?
Sorry?
Have humans been levitated with magnets yet?
If they have levitated, to the best of my to the best of my knowledge, people never have levitated with like that.
How strong of a magnet would you need for that? It's quite massive.
I think superconducting magnet, it can go to tens of Tesla, and field is sufficient. I suppose the main problem is volume. So you need big volume. The largest magnets which are used in real application, I think, is MRI. It's where you need to put a person inside. And so they need big volume and they need big gradient. I suppose there they use around 1.5 Tesla. And it's not sufficient for levitation. So, okay, so probably we need still much larger field, yeah. And large volume, and I suppose it's simply very hard to realize. Good, okay. Then let us switch to paramagnets. So yeah, what we have to keep in mind about diamagnets that it's not correct to say that they are non-magnetic, but it's correct to say that there is no magnetic moment as long as there is no applied magnetic field. But there is a class of materials, paramagnets, where you always have this magnetic moment, independently if there is field or not. And if you will take paramagnet and you will apply zero magnetic field, there will be KBT energy, so thermal energy, which will bring chaos into the system. And we will have it all randomly distributed. Therefore, if you will calculate magnetization, which is average magnetic moment, for each magnetic moment pointing in one direction, there will be some which compensates it. And the magnetization will be equal to 0. Now, what you can do with paramagnet, you can apply magnetic field, And in this case, you see it's still chaotic, KBT is still here, but they already tend a bit more to point in that direction, like it's shown here. As a result, if you will average everything, magnetization won't be zero anymore. And if M is not equal to 0, then our susceptibility is not 0. Yeah? So it means that there is a magnetic response of a media to the applied magnetic field. If your field will be very big, much larger than 1 Tesla, you can get situations that they all will be magnetized parallel. And this, in reality, we do have the situation in our labs. Scientists have it in their labs. But usually you go to smaller temperature, just decrease KBT. And then it's very easy to magnetize it with 1 Tesla or so, which is already quite big field, but still easy to achieve. But let us have a look which field you need to apply in order to magnetize it at room temperature, 300 K. Let's imagine that you have 1 Tesla field applied. Magnetic moment, the easiest what we can do, we can take it as a bore, magneton bore, and then you just plug it in this potential energy, and you come to the value 9 10 to the power minus 24 joule. Now let us see what is KBT. 300 K, KB Boltzmann constant. We plug everything in, and we have 10 to the power minus 21. So 1,000 times larger energy. So it means that if you will apply field of 1 Tesla, you need field like 1,000 times larger, like 1,000 Tesla, to be able to magnetize it at room temperature. And to the best of my knowledge, it's not possible. In lab, I think you can get 50 Tesla. Some experiments I heard that people use some explosions in order to achieve larger fields, but for very short time. But in simplest case, you cannot magnetize paramagnet at room temperature. So here, by the way, you see white, yes, that majority of materials are paramagnet. And now I would like to make a little detour to these guys, which are named lanthanides, or rare earth ions. You see some of them paramagnetic, some of them are antiferromagnetic at lower temperature, and some can even be ferromagnetic at even smaller temperatures. So principally, this is a very interesting class of materials, which is also intensively investigated in research. And let us talk about it. Why? Because this is very special material. If you will have ions, which are usually solid bodies, so there are ions inside, like europium 3+, for example, terbium 3+, and so on. And if you will look on the radius of these ions, it's more than 1 angstrom. It's big. It's already heavy material, big atom, and radius more than 1.1. And these shells, which are outer shells, they are usually coming from 5s2 and 5p6 orbitals, from the outermost orbitals. And particularly these orbitals are responsible that our body sticks together, that all these couplings and everything, or if it's metals or electrons, are releasing and so on. But atoms which are responsible for magnetic response are 4f electrons. Not atoms. And they have diameter 0.3 angstrom approximately. So it means that these orbitals which are responsible for the magnetic response, they are localized and they do not interact. Why is this important? Because solid state physics is very complicated field. As soon as orbitals are overlapping, or you have some coupling, or you have different physical mechanisms, you usually cannot use atom physics to calculate any simple physical parameters. So in this case, we want to calculate just magnetic moment of 1 atom. And if you will go to nickel, iron, or any materials, usually you cannot do it. So atom physics cannot give you the answer. You need to develop models. You need band model if it's free electrons, or some other more complicated. And the only principal class of materials is rare earth ions, where you can calculate magnetic moments simply based on atom physics. So you consider more or less these atoms independent. You calculate, you measure, and you see that they agree. And so how this magnetic moment is found is simply G factor, which depends on S, on L, which is S spin of by L is orbital momentum, your total orbital momentum. So you can calculate this for any of these ions. You can calculate this G factor, and then that's a formula how you can get magnetic moment from your rare earth material, and of course times mu b. So magnetic moment of each electron is magneton Bohr. So that's the main idea behind rare earth elements. And now I would like to come back to the question of paramagnetism and how we can get susceptibility. Here susceptibility, and this one can be obtained the following. So we more or less considering this ensemble of atoms, of magnetic moments, let's say, put it like this, many of them, yeah, and then we place them in magnetic field B, and we take into account potential energy. And so again, formulas can be found in Krishnan, but for me, the message is that you don't need to invent anything very special. It's just classical Boltzmann statistics, where potential here exponenta minus E potential divided by KBT. So you see that we already have in the formula this competition between potential energy, which is given by magnetic, when we place magnetic moment into field B with KBT. And then you need to integrate all this over the large ensemble of such magnetic moments. And as a result, you will get so-called Curie law, that He paramagnets is equal M over H equals this value. So what we see here, mu0, fundamental constant, and it's a number of magnetic moments per unit volume. So it's not number, it's density, KBT, temperature, and magnetic moment squared, which can be magneton Bohr in simplest case. And then if you will take all these parameters, everything except temperature, will put it as C, you will get very simple formula that susceptibility of paramagnetic material is some constant divided by temperature. So in the very first lecture, it was actually 2 meetings before, we discussed this Langevin theory of paramagnetism. And here I would like to add that this formula is obtained for the assumption that magnetic energy, this magnetic moment of electron times external field, is smaller than KBT. Because as you see that if you simply go to T equals 0, then susceptibility goes to infinity, which is unphysical, of course. And then what I forgot to mention is that there is assumption. So the full version of this is written with cotangents hyperbolic, and then it saturates. So the largest magnetic moment which you can obtain in paramagnet, when, as we discussed, will be simply number of magnetic moments you have in your system, or density, normalized by volume, times magneton Bohr. So there is always saturation. You cannot achieve a magnetic moment larger than it is already in the system. Yeah, and this principle describes exactly what you have seen in the previous picture. If your temperature is 0, then or small, then susceptibility is very large. So it means you apply small field and you can magnetize your body. If temperature is large, then you need to apply a larger fields, H, in order to magnetize your body. So very simple, but dependence is inversely proportional. Here you see a text, it's about superparamagnet. So superparamagnet is critical for hard disks because when you write data in a hard disk, you want to make your domain, which keeps your data smaller and smaller, but they are using polycrystalline material. So it means that in each domain there is another number of magnetic grains. And then it's always a place they're trying to make this grain smaller and smaller, and at some point they come in so-called superparamagnetic limitation, because at some point you can start to consider each grain as magnetic moment FM. So more or less all the same like we have in atom physics, but now you take magnetic moment not of individual atoms, but of already some macroscopic clusters. And yeah, they have found a way how to make hard disks better and better. So now we are storing in terahertz range. Good. I want to show you one more interesting video. I want to show you the difference between paramagnet and diamagnet. But before I do this, I need to make a little detour and to come to molecules. This is not solid body, but let us consider molecule of nitrogen. And so we see nitrogen, its atomic structure is like helium, plus you have then two s2 electrons fully filled, and unfilled p orbital, 2p3. Boiling temperature of nitrogen is 77 Kelvin, and that's how this last orbital is shown. So we don't discuss here Hund's rule, but they force electrons to occupy this position in these three states. So spin up, spin up, spin up in such a way when you put this in different positions, you decrease Coulomb interactions. They are not sitting together because electrons are charged. In such a way, system simply minimizes total energy. And that's how orbitals look for one n and for another n. But if they are coming to molecule, there will be hybridization. So instead of this orbital, we will have all these orbitals. And now we need to fill them with 6 electrons, 4 coming here and 2 coming here. And you see it's important for us that this orbital is fully filled, spin up and spin down. We can put 2 electrons because we have additional quantum number. Yeah. And Pauli exclusion principle allows us to put 2 electrons in one orbital. Therefore, if we have uncompensated, so we have no uncompensated spin, then it's diamagnetic. So why, like noble gases are diamagnetic and so on? Because you have fully filled orbital, for example, then it's diamagnet. There is no uncompensated magnetic moment. Good. Let us switch now to oxygen. Oxygen is, although it's much more important for us, yeah, in air, I think 70-something% of air is nitrogen, and around 20% is oxygen, but particularly oxygen is important for us that we can function. And it's very much similar to nitrogen, with the only difference that we have one extra electron here, and our orbital is 2p4. And what is from practical perspective important is that boiling temperature is slightly larger than boiling temperature of nitrogen, so it means that you can use liquid nitrogen to make oxygen liquid. So again, atomic model here, Also at electrons here, 4 and 4, the same kind of splitting of energies. We fill this orbital, and 2 electrons are coming here, and again, they are coming in such a way. So it means that we have here 2 uncompensated magnetic moments, 2 magneton Bohr. This is a paramagnet. There's diamagnet, and here's paramagnet. And let us see what does it mean, this fantastic experiment from Oxford.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled door. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet, and then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
So now you know how to get liquid oxygen. Alcohol is produced in a similar way. So now it's simply nitrogen, which is diamagnetic, and you see that it's flying away, or simply doesn't feel at all magnetic fields, or if there is a feeling, then it's repulsion, and very weak one. And that's how it looks, liquid oxygen, which is magnetic, which is paramagnetic. You see it sticks. Very fun, yeah, only one electron difference in an atom and completely different behavior in terms of response to magnetic field. And it's really cool that I can use YouTube and don't have to, because it's a lot of work to reproduce this experiment in a lecture. And with YouTube it works very smooth. So let me just go to the next one. Other questions to the paramagnetism? General idea is clear. Good. That's sufficient fast. Spin waves have never been studied in diamagnets. In paramagnets, there is such term paramagnets. We even starting now, the rest is here, starting now to go into this direction and trying to see if we can work with spin waves in paramagnetic materials. But usually, ferromagnets are used for investigation of spin waves. And very popular nowadays is, and very hot research, spin waves in antiferromagnets. They have fantastic properties. The only problem that antiferromagnet, since it has compensated sublattices, usually it's very hard to excite and to detect spin waves. Therefore, it's a fantastic field for theorists and not such an easy field for experimentalists. But let us start now with the same story. So you remember KBT, energy, 10 to the power minus 21 joule, yeah? And then if you would need to saturate it, so here it's written in field H, which is like 2.5, 10 to the power of 9 ampere per meter. But as we said, let's say it's 10,000, or it's 1,000 Tesla, or it's 10 to the power of 7 Ørsted. If you use Ørsted, so it's an unrealistic, very big field, and you cannot saturate paramagnet. But if you go to reality, people have found some class of materials where you can magnetize it with field as small as 1 ampere per meter, so 9 orders of magnitude smaller. And the question was why? And the answer to this question gave Weiss. So that what we are discussing here is Weiss' theory of ferromagnetism. But let me just tell you the main idea. And his first hypothesis was that in some materials, the formation of magnetic clusters, so-called magnetic domains, take place. So it means that for some reason, you name it, some internal molecular field, magnetic moments of atoms are pointing in the same direction. They stick together. And then he has introduced these domains and described magnetic moment, magnetization in terms of these domains. Because what happens, imagine that within one domain, you have 10 to the power 6, 10 to the power of 9 such moments. And then when you will apply even such a small field, 10 to the power minus 3 Tesla, you see that energy of such domain will be 10 to the power minus 18, which is already 3 orders of magnitude larger than KBT. So if you have such domain, which are all magnetic moments are staying parallel, then you can explain experiment. So what happens when you have these domains? Field B equals 0. Domains are pointing in all different directions, and magnetization, the total magnetic moment, also can be 0, because for each domain you can have one which compensates. Story is getting interesting when you apply magnetic field. Then we have two mechanism. So first of all, smaller one kind of magnetization tries to tilt a bit in the direction of applied field to magnetize energy. But what is in reality usually happens is that domain which had proper orientation, and proper means oriented along the applied magnetic field, it starts to grow. And it grows, and pushes all other domain outside until we apply some so-called saturation field, when we have single domain state, when all spins are pointing in the same direction. And this is something which you know very well, probably from school. It's hysteresis curve. So if you have, here we plot magnetization, and here we plot applied magnetic field. No magnetic field, magnetization is close to zero, let's say. Then you start to apply magnetic field. Domains are getting larger and larger, so magnetization is increasing. And then starting from some point, you reach saturation when there is single domain level. And when you increase field further, nothing changes in the system. All spins already point in the same direction. Here, of course, you can see such little steps here, but the idea is clear. What happens then important afterwards, when you start to decrease field, you're coming to this point, but you do not go this direction because your system is magnetized and it stays magnetized. And what happens then, you will reach this point, and this magnetization, which you reach in a magnet for zero applied field, is named remanent magnetization. And then when you want to bring magnetization to zero, you need to apply field in the opposite direction. You go here. So you need to apply this intrinsic coercivity. So coercivity field HC in order to get it back to the M. And then you just draw this hysteresis loop. And that's very important. So there are soft magnetic material with this small coercivity and large MR. There's hard magnetic materials which are used in our permanent magnets with a broad hysteresis loop. So we want to keep this HC large. And that's also how our data storage in hard disk works, yeah? Because after you magnetize it, you can have this state for logic 1, or if you magnetize it in the opposite direction, you have this state for logic 0. So you switch it back and forth. So this hysteresis loop is very important. But it's just to refresh your memories what we are talking about here, what is a magnetic domain. But we are coming back to Weiss's theory of ferromagnetism, and he said actually two postulates. Okay, first postulate is that we have these domains, that magnetic moments are oriented in the same direction. And second, and he said that these domains are formed by internal field, or molecular internal field. It was empirical formula, so there is nothing, there was empirical theory, there was no quantum mechanics at that time. So nowadays we know that what is staying behind this internal field is exchange interaction, so it's part of Coulomb interaction, which depends on spin, which can be described only by the quantum mechanical principles. But he just said that there is some internal field, and this field is proportional to magnetization, M. So he just made this formula Q times M. That's second, his assumption. And this model works good to describe ferromagnets. So what we need to do afterwards, we just take the same theory for paramagnets, which you had already, but instead of field H, you plug in H total, which is H plus H internal, where an H internal is simply proportional to M. Then your potential energy is equal mu 0 M H plus QM. And yes, and then you just more or less can even use the same formula for susceptibility, which we had for paramagnetic material. You remember by C over T. But now if you take into account internal magnetic field, you will get this formula that is CT minus QC, or CT minus TC. And TC is our Curie temperature, which we have seen already in the periodic table of elements. C is just constant. So what does it mean? It means that here is a temperature scale. Here is magnetization. And here this picture is a bit tricky, so be careful. There are two y-axes. Left side here is magnetization, and right side here it's inverted susceptibility, 1 over height. And if you stay in the temperature smaller than Tc, then you do have spontaneous magnetization. So in the absence of magnetic field, your magnetization is not equal to 0. That's what's very important. And this depends on temperature. If your temperature is 0, then you will get saturation magnetization. So largest magnetization you can get in the system. Then when you increase temperature, you still have this internal energy associated with internal field, but KBT starts to play a role. Therefore, your magnetization drops down, down, down until it reaches Curie temperature. And afterwards, for the temperatures larger, it behaves just as a standard paramagnet. Therefore, here the behavior is simply 1 over high. This susceptibility. And yeah, so here you see Curie temperature and the theta C, it's Curie-wise constant. In majority of the cases, it's the same. It depends. It's a little different. Some cases can come from this point from the fact that size of domain changes when you change temperature. But in our course, we just consider Curie temperature. So, and this is classical and empirical model. What we do when we want to make step closer to reality. We again coming back to quantization, so we need to take into account quantization. So it's a brilliant model, so-called. But the idea is very simple: that this magnetic moment m is just variable which can take any values. But if you go to reality, of course, you need to take into account that m is quantized. It depends on the total angular momentum y, and on the lambda factor g, which depends on spin orbital momentum, total momentum. And then if you will rewrite this by theory already with taking into account quantum mechanics, you will get this formula for Curie temperature. Mu0 g mu Bohr y plus 1 and times q. Q is still staying here just as in proportionality factor, which we don't know, but in reality, as I said, exchange interaction staying behind this q. Typical ferromagnets or magnets: iron, cobalt, nickel. 3 materials which show ferromagnetic behavior, show spontaneous magnetization at room temperature. Gadolinium can show. So there are in reality many more different materials. So for example, for spin waves, people often use permalloy. It's nickel iron. It's such a soft magnetic material with small magnetostriction where it was developed originally for. And there are hard magnets like this niobium iron boron. It's one of the magnets, commonly used magnets, with which we apply and usually also. This is a strong, good magnet with very good characteristics like terms of remanent magnetization, coercivity, Curie temperature of these materials. You see, for iron, cobalt, you need to warm up it to more than 1000 Kelvin in order that it stops being magnetic. But this temperature changes. For gadolinium, yeah, it's close to room temperature. And yeah, for niobium, it's 600 Kelvin. So much about ferromagnetism. We will still have to speak about exchange interaction, but at this stage, other questions to Vasily. Yes, please.
I have a question to the slide of the table. The table of the magnets.
Magnets, the next one. Mm-hmm.
Yeah, here at gadolinium, there is like in brackets 0 Kelvin, but like the column is for 20 degrees Celsius. Is this a mistake or is there a reason?
I would assume there is a reason. Let us have a look. What do we see in this table? Yeah.
Could you repeat the question?
Yes, I would like to repeat the question. It was gadolinium. Yeah, you said. So for gadolinium in that column there was written values for 20 degrees of Celsius for room temperature, but in the brackets there was staying 0 temperature, 0 K. And Rostislav is surprised, why is it? Let us find gadolinium. Light and I? Mm-hmm. 292, so it's all good. So here it's also shown as a ferromagnet with a Curie temperature slightly below room temperature. Now let us come back to the table. Oops. Yeah, I suppose they still plugged it in because it can be ferromagnetic at temperature close to room, but formally speaking, at room temperature it's already paramagnet, and this saturation magnetization should be zero. Therefore, I assume what they did, they have shown you just saturation magnetization, which can be at zero temperatures, like how strong it can be magnetic, yeah? But it's not, this value is of course not correct at 20 degrees Celsius. Okay? Yeah. David says it's good that I have answered. We will cut it off later. Good. So I have 10 minutes more. Let us speak about interactions. So why, how these magnetic moments can interact. And the first interaction is dipolar interaction. This is something which we know very well. It's from when we were kids, we were playing with magnets, maybe with compost needles.
Still not sure about that.
I apologize for that. So we have the dipole-dipole interaction, and it's simplest physics. So like we all studied in electrodynamics, when you have two dipolar magnetic dipoles, shown here MI and MJ, there will be some distance between them, RIJ, some vector. Then there will be dipole-dipole energy, which is shown with such a complicated formula where you have R to the power of 3, R to the power of 5, EJ is a vector, and here you see magnetic moment MJ, MIMJ, and here 2 times. This comes from the fact that simply each magnetic dipole creates a field around, which is given by this formula, which is a field created by one dipole. It depends also R to the power 5, R to the power 3. And of course, you need very carefully to take into account all vectors. And what we need to keep in mind, the dipole-dipole interaction has magnetic nature. So compared to exchange interaction, which will be next one, it's very weak, but it's long distance. So this magnetic field goes over a long distance, therefore they feel each other, these magnetic compost needles. And here again, just a nice demonstration, since we are tired already a bit. Let us have a look, a very nice demonstration of dipolar energy.
Large magnetic line of force demonstrator has lots and lots of compasses. You slide the magnet, horseshoe magnet, right in like this. Slide the removable panel back in, and you can see the magnetic lines of force are very visible. It's quite a big demonstration. Here you have the second part of the magnetic lines of force demonstrator. As you can see, it has a removable panel here, and we simply slide that into the slot. And the included magnet, cylinder magnet, is placed centrally in the device, and then the panels put back into the device. Now you can see the magnetic lines of force are very prominent. It's a very neat demonstration.
Good. So you have found how dipole-dipole interaction works. You have seen how dipole-dipole interaction works. And also a very nice demonstrator where we can see this field lines. Yeah. Our next step will be to explain exchange interaction. But we need to be very fresh for this, because that's not the easiest part. And afterwards we will discuss magnetism in metals and alloys. Since we already considered a lot of material, so I really packed many lectures into one just to give you an overview of the materials, which is important to know, to understand better spin waves later. I suggest we shift the direct exchange interaction already to the next lecture. Other questions to today's material? No, everything is good. Okay, then thank you very much for your attention. So now we are coming to exchange interaction. So originally exchange interaction was introduced by Heisenberg. So principally we are discussing here Heisenberg model, or it's also named direct exchange interaction. The easiest way to explain it would be if you will have a look on the molecule of hydrogen. So principally two hydrogen atoms with one proton here and one electron around, rotating like that. And in order to describe this molecule, we need to introduce a wave function of electron as psi A. So it's a function of electron located at the A, atom A, as a function of coordinate R1, starting from this point, And psi B, the same for the second electron, taken in the around second nucleus. And now let us have a look, and what we need to do, principally, we need to derive now a wave function which describes both electrons together, which describes molecule. And for this, there are mathematically two ways. You can describe it simply psi A plus psi B, or psi A minus psi B. So you sum or difference, but it has also clear physical meaning, because in the first case, you will get a so-called bonding state. What does it mean? So here is psi function of the bonding state of this molecule. And you see here in the middle, we have non-zero function. So it means it's this one plus this one. And here we have non-zero value. Why it's important? Because if you, as we all know from quantum mechanics, if you want to know the probability of electron to be in some position, what we need to do, we need to take psi squared. So this is our probability, and you see that in the bonding configuration, the probability that electrons are in between these two atoms is, two nucleus is high. And that's very important because in this case, that's how covalent bonding works. In this case, electrons, they are negatively charged, and nuclei, they are positively charged. Of course, there is Coulomb interaction. So principally, it's repulsion energy. So nucleus, I would like to stay far away one from another because they're positively charged. But if in between you put negatively charged electrons, it's stuck. So it more or less helps to stick it together. And in terms of energy, here you see energy as a function of R, where R is the distance between two nucleus. You see that for bonding states, we have a minimum. So there is certain distance where really energy is minimized. So it's good for system is stable. And we have here electrons in between then our positively charged nucleus. So this is bonding state. But if simply mathematically you will find your wave function as a difference between these two, you will get to this psi function, which has 0 at middle, and then probability that you will get electron just in the middle is also 0. It means that there is another state when electrons prefer to stay outside of your nucleus. So one is here, one is here. In this case, of course, energy is larger, so it's not comfortable situation, not the optimal situation, but it can exist if you take into account other contributions to energy. So we have bonding, anti-bonding, and then usually it's visible like in the formation of two energetical levels. So if this is energy level of your electron in one separated atom, and when you put them together, you will get two atoms, two states. For bonding, it will be smaller, and for antibonding, it will be higher. So now the question is, so we understood more or less that we can have two states, and we were operating mainly with the charge of electron and Coulomb interaction. Now the question is how spin relates to all this. Because so far we discussed nothing about spin, but for magnetism, spin is very important. And here, in order to, principally you should understand that exchange interaction, it's a part of Coulomb energy, so it has electric nature, and but that part of Coulomb energy which depends on the spin orientation. How it happens, how we can put it together, we need to go to Pauli exclusion principle. So principally, Pauli exclusion principle is a principle which couples all these things. Imagine that we have anti-bonding state, so that we have bonding state when two electrons are sitting in between. And Pauli exclusion principle tells us that two electrons cannot be in the same position with the same quantum number, so more or less with the same state. So it means that there is only one way how we can put two electrons in the same place in space. It's to give them different spin orientations. So it means that if you have bonding state, ground state, the only way it can satisfy Pauli exclusion principle is that it should be antiparallel electrons. And then we are immediately getting this situation that we know what will be the state of electrons here, spin orientation of electrons in this place. Now, how about antibonding state? When one electron is here and when another electron is here, and kind of going from classical principle, you would say that there is no any relation, conditions on spin, yeah, because they do not feel each other, they are far away. In reality, it's not the case, because in quantum physics, if to define Pauli exclusion principle properly, it's not simply that we cannot put two particles in the same position with the same quantum numbers, but it's a bit more general, that if you're working with fermions and electrons are fermions, then the exchange wave function, so when we change the replace electrons one with another, that's why exchange is named here, we will get this wave function should be antisymmetric for fermion. What does it mean in practice? We have here to speak about two wave functions. One is a coordinate wave functions, and you have seen it. This is for antibonding, antisymmetric, and this is for bonding symmetric. But in addition, we need to take into account wave function which describes spin state of your electron. And this one, I do not draw it, but principally at the end of the day, you need to multiply one with another. The spin wave function is shown here simply schematically with the spin orientation. And for example, we understand well the bonding case, and you see that this wave function is symmetric. And now we want to multiply it with something, and it has to be antisymmetric because electron is fermion. What does it mean? If we take symmetric function, we need to multiply it with antisymmetric. It means that this and this arrow should point in the opposite direction. Then we have antisymmetric state. When you multiply this with this, the total wave function will be antisymmetric. So the Pauli exclusion principle is satisfied. Now let us have a look onto antisymmetric coordinate wave function, this one, for antibonding state. You see that it's already antisymmetric. If you will multiply it with an antisymmetric spin function, you will get symmetric one. Therefore, spin wave function should be symmetric. So it means that in this case, you multiply symmetric wave function with antisymmetric, you will get it antisymmetric, you satisfy Pauli exclusion principle, and it gives us the information that when two electrons, one here and one here, they still coupled, their spin information is important, but they should be parallel, like it's shown here. So it means that when electrons are inside, they are antiparallel, when they're outside, they are parallel. And this brings us to important conclusion that in the ground state, it's also named singlet state. we have antiparallel electron configuration, and in the first excited state, there is a triplet state because they are parallel. There are three different states when both spins up, both are down, or superposition of both, and we have here triplet. So that's the main idea how we managed to combine exchange Coulomb interaction with Pauli exclusion principle, and as a result we've got situations that depending in which state electron is, we can get, so this spin also will be predefined. The next is very simple, formal steps. If you want to know now what is the exchange interaction energy, what you do, you have one energy for one state and you have another energy for another state. And the difference between energy of triplet state minus energy of singlet state will be given, named exchange energy. Very simple. So this difference in the energies is defined by exchange energy. And this exchange energy actually can bring our electrons up, yeah? So because you should take into account not only potential energy of electrons in a molecule, but also this additional contribution from exchange energy. Then Dirac has written this famous Hamiltonian for exchange interaction, and it's written usually in such form, minus 2, sometimes depending what is staying in this yacht. Sometimes people use 2, sometimes not. It's slightly different constant. But important is that there is this exchange interaction, more or less this parameter, times SI, scalar product S yacht. So it means that now, and these are vectors, these are our orientation of our spin. And yeah, so this is how we describe interaction between neighbors, because there are other types of interaction, super exchange, and other types. There is a Doloshensky-Maria interaction, which is also part of exchange interaction, where you will have cross product here, so it wants to keep system like this. But here we discuss only direct exchange, Heisenberg model, and this one would like to minimize energy, so we always want to minimize energy by minimizing, in this case, it means that our spins should be either parallel or antiparallel. In which case we have what? For example, our integral, so this integral, exchange integral yacht can be positive, it can be also negative. If it's positive, then let us have a look. This one is positive, so we want to here stay in minus. That's why we want to have this part as large as possible, because then it shifts energy, total energy down and down. It means that in this case, if this one is positive, we want to keep this one also positive and maximal. And maximal for it's for scalar product, yes, so it's cosine. So it means that we want to have these two spins to be parallel. That cosine is equal 0, then it will be 1. Yacht is positive, this part is as large as possible, but with negative sign. Therefore, if our exchange integral is positive, we are speaking about ferromagnetic state when all spins are pointing parallel. If exchange integral is negative, then in this case, we will minimize energy by bringing -1 from this state. So we want still, so it means this minus disappears, but still in order to minimize energy, we want to have it negative. And for this, we get this -1 from a cross product of these two values. And of course, then cosine will be -1 when we have 180 degrees, which means that spins are pointing in the antiparallel direction. And antiparallel direction means antiferromagnetic state. So we don't go here into the details, but usually antiferromagnetic. Yes, please?
It's a scalar product, no?
Yes.
That's cross product.
It's scalar product, yeah. I said
You said cross product.
Sorry, yeah. It's scalar product, yeah. And then we want to have it antiparallel. So where do we have antiferromagnetic state? So maybe it's a bit confusing here. Usually in reality, it appears in more complicated materials with different sublattices. When there are different sublattices, and then also due to other mechanisms. Magnetic moments in one sublattice is equal to magnetic moment in another sublattice, but anti-parallel. And then, if you take this material, it's antiferromagnetic. It doesn't behave like magnetic material. You don't know that it's magnetic, but in reality, it's as magnetic as a ferromagnet. It's very modern. Also, antiferromagnetic magnonics is popular, hot nowadays, but it's out of the scope of this lecture. So. And it's still mainly theoretical because it's very hard to excite and detect spin waves in antiferromagnet. Other questions to direct exchange. Why it's important? I made it very quick for people who are watching YouTube. There are recordings in advanced material lecture where the same material, the same slides, but explained in a bit with a bit more details. But why it's important for us? Because it explains why magnets can be magnets. Yeah, so that's actually this internal Weiss field, which he introduced without understanding what is that. It's nothing else as the COT. This exchange interaction is providing this internal field, which keeps our spins parallel, that it forms these domains. Otherwise, we would not have spontaneous magnetization in any material. Good. Another very quick lecture on metals. So everything what we were discussing before relates more to atom physics, yeah, or like two atoms together nearby, or to isolators. But when we are coming to metals or alloys, we need to develop and to use other models because everything is different in the metals. We have electrons which are unlocalized, which can propagate in the whole volume of your body. And for this, we need to operate with so-called energy bands concept. And for magnetism, energy bands is actually named Stoner model of ferromagnetism. Coming back to our periodic table of elements, the point is that these three guys, iron, cobalt, and nickel, they are metals. So it means that if you want to understand why they are magnetic, we need to go into Stoner ferromagnetism. Here, I show you different elements: Nadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. And here you see how many electrons they have in 3d and 4s orbitals. Simply you add always one electron on top. It's very fun, yeah? So you always add one electron in completely new material with completely different properties. That's why solid state physics is so interesting. And here you have how many of these electrons are in 3d orbital, how many in 4s orbital. That's how configuration. And you see that it's all very similar, but it's not clear what is so special about particularly these three guys. Why these three are magnetic, and manganese and chromium can be antiferromagnetic at lower temperatures, but copper is not magnetic, all others are not magnetic. But they are all very similar, and let us try to understand why. In order to do this, very briefly refresh your memories about the what is energy band model. What is the main idea? As you probably know very well. But as we discussed already in this example of molecule of hydrogen, when you have one electron, there will be one energy level. As soon as you put two of them together, they interact, you will get two energetical level, bonding and anti-bonding state like it's shown here. Or if you get used to resonators, you know that as soon as you put two resonators, any resonators close to each other, they will be split in energy, anti-crossing, so-called phenomena. So that's more or less the same. If you now, instead of two atoms, you use something like benzoyl ring, I think it's named, so more complicated structures, you will have more energetical levels depending on how many atoms you have that interact one with another, or electrons from these atoms fill each other. Then you can go to more energy level, and then we are coming at the end of the day to metal, where all electrons are in the space in your sample. And it means that you have as many energetical levels as many electrons you have in the system. And the distance between these energy levels will be then you take few electron volts, let's say, if the largest energy is a few electron volts, and you divide it by the, you can simply take Avogadro number, 10 to the power 23, as the total number of electrons in 1 mole. And then when you will divide it, you will see that distance between each energy level is 10 to the power minus 23 or so electron volts, which means a very, very huge, small difference, practically zero. And you cannot anymore describe anything in your system operating with separate energy levels like it was done here. Instead, people defined a concept of energy bands, and then we work in completely different model where we are not anymore describing any energy, but we describe how many electrons are in each band. Yeah? And then that's how we describe conductivity. Some materials are conductive, some are isolators. Semiconductor properties are described perfectly with this concept, and so on. How it looks in practice, if you will take some material and then you plot energy bands as a function of d, where it's a distance between nucleus. Then if you have very large d, then you're dealing with independent energetical levels, which means just atom physics. Yeah, you have 1s orbital, 2s, 2p, 3d, 4s here. And then you start to bring them closer and closer and closer, and these outer shells start to interact. They start to fill each other. And in this case, you see the formation, first of all, 4s is the largest orbital. We see the formation of band, it's getting wider and wider and wider. Then when you go further, 3D also forms that instead of single level, you will get formation of a band, like it's shown here. And these inner shells, they still have like classical atom physics. They are not interacting because they're small, they're localized. So we are speaking principally then about localized electrons and delocalized electrons here in 3D and 4s. Or usually 4s are delocalized, 3D are localized still, but in many effects we need to take into account partial delocalization of 3D and partial localization of 4s. So principally physics here is getting a bit complicated, but basic principles we can understand. Good. So that's how we introduce band. And from slightly different perspective, in the solid state physics class, Core 10, we start with free electron model. So it's another model. We need to merge them at the end of the day together. But at this stage, people, when they were trying to describe transport properties, first of all, heat conductivity, electric conductivity of metal, they started with free electron model, which means box full of electron, like ideal gas. And they don't interact, and we just describe their kinetics. Principally, we are taking into account only kinetic energy of electrons. So then here I just give you final result. If you consider 3D gas of electrons, then you will have density of states. So density of states functions, this G here, it shows you number of states per energy. So how many electrons of given energy you can have. And this one, for 3D case, it looks simply a square root of energy, like it's shown here. Yeah. But usually, it's only states which exist, that your electron can occupy. But it doesn't mean that the state will be occupied. If you want to know which states will be occupied, you need statistic. In this case, since electrons are Fermi-Dirac fermions, you need to take Fermi-Dirac distribution, shown here with this F, which means what is the probability, so simply from 0 to 1, that state of energy E will be occupied. And here, inside you have energy of your electron, you have chemical potential, and you have KBT, KB Boltzmann constant, and T temperature, and +1. Magnons are, we will briefly discuss, are bosons. They are quasi-particles, usually real particles like electron are fermions, and quasi-particles are bosons. So then you need to use Fermi-Dirac Bose-Einstein distribution, where here stays minus. But physics is very different, although you change only one sign. But coming back to fermions, we have here plus, and what is the physical meaning? Very simple. If your temperature is equal 0, then your distribution will be just step function. Everything below so-called Fermi energy will be 1, that state will be definitely occupied, and after Fermi energy, it will be 0. And then when you multiply G with F, like it's shown here, you will get such characteristic for 0 temperature. Here is also staying the chemical potential. So pretty often chemical potential is equal to Fermi energy. But strictly speaking, Fermi energy by definition, it's the energy, largest energy in the system that is filled at the ground state. Ground state means temperature is equal to 0. So it means you take this curve, largest energy which is filled is our Fermi by definition. Chemical potential mu, it's energy which you bring into system or you take out of the system when you change the number of particles, number of electrons in your system by 1. So it means that if I have this field state, I put in one more electron, its energy will be definitely Fermi energy because it cannot go here. Here all states are filled and our electron cannot jump here. So any new particle will be placed just next to it. And therefore, chemical potential is equal to Fermi energy pretty often. Coming back to Fermi-Dirac distribution, so what happens if our temperature is not equal to 0? In this case, you see that that's for one temperature, T1, and if temperature is getting larger, it smashes this part. And the width of this part where you have this smashing is approximately kBt. Yeah, so it's given by the temperature, this is energy, and that's extremely important for us because not only for magnetism, but for general properties of solid body, because you see here there are many electrons, but they are all in occupied and fully filled states. If you have one electron and then you, for example, apply voltage, it wants to increase its energy, potential energy. It wants to jump to another state, but it cannot because there is staying already another electron, which has the same spin and the same energy, all the same quantum numbers. As a result, all these electrons, although there are so many of them in the system, they do not contribute to properties of a body. They principally are just staying there. Important for us are electrons which can change their state, particularly in this region kBt. Because this electron, if you take one here and if you will apply voltage, it can jump to this state. Or the electron from this state can jump back because these states are not fully filled, there are more spaces. That's why we will see it also in magnetism, but in general, we need to keep in mind that particularly the number of electrons at the Fermi energy level is important to describe real properties of a solid body. Good. And the rest is easy. What we need to do, we need, first of all, to split electrons into two parts, because for us spin is important. Therefore, what we do, we just say we separately consider electrons with spin up, and separately spin electrons with spin down. So we more or less plot this graph 2 times, and here you see GF divided by 2, because we understand that we consider here only half of electrons, and half of electrons with spin down. And in the simplest case of normal metal like copper without an applied field, this will be symmetric. There will be no difference between spin up and spin down electrons. Good, so now we are ready. We refreshed our memories about energy bands and free electron model. And now what we need to do, we just come into Pauli paramagnetism, which describes susceptibility of paramagnetic material if it's metal. Here you see the same E squared dependence. Now it's turned 90 degrees, the graph. And if you have no applied field, then principally this is both the spin up and spin down dependencies behave like shown with dashed line. But as long as now you take paramagnetic material and you apply magnetic field, in this case, energy, as we all know already, is minus m scalar product B, like it's shown here. And it means that if our electron spin direction is anti-parallel to B, energy will be increased because of this sign. This parabola kind of, it moves up, but for spin down. For spin up, which points in the same direction as field, which is favorable direction, energy will be decreased, it moves down. So it means that this is more comfortable situation. Like it's shown here. That's what happens in paramagnetic material in the assumption of free electron model. And then it's very easy to calculate the magnetization of this material. Because what you have, you know that there is, each of these electrons carry magnetic moment of magneton Bohr. And you know that this parabola is moved down, so it means that this distance, this width of this part, is larger here than for spin down. It means that you will get small disbalance between the number of electrons with spin up and number of electrons with spin down. And as a result, you will get magnetic moment. So you just need to more or less calculate what is the difference in number of electrons, and then you will get immediately magnetization. So I just jumped, so it's all, if you want to go to details, you can see how Krishnan did it. But principally, that is the final result for susceptibility, Pauli susceptibility. So it's magnetization of your material divided by the applied field. So if there is no field, there is no M, as we know already. And you see that it is proportional to the density of states at Fermi energy. So very important, how wide is this part here? Yes, how many electrons at Fermi energy you have. And if you have small number of Fermi electrons there, electrons at Fermi energy, then it will be, then susceptibility will be very small. If you have a lot of electrons here, your susceptibility can be large. Other question to Pauli. Paramagnet. Idea is, I hope, is simple, clear, or more or less. Okay. For us, it's important, because you cannot describe magnetism in metals in a different way, to my understanding. Because this part about susceptibility in metals. So when we work with metals, where there are conducting electrons, we switch to completely new models, where we deal with bands and so on. And Simon has found that there is a temperature dependence here in the system, and because for paramagnets in Landrew's model, it was large dependence of susceptibility onto the on temperature. And here we see that it's not dependent, or to be more correct, it's practically independent. The only way where this dependence in this formula can be is a very weak one here, but it's also an open question because, strictly speaking, this G at the level of chemical potential mu is equal 1/2. So it also doesn't depend on temperature. But if you work, so it means if you work in the assumption that Fermi energy equal chemical potential, then even here there is no temperature dependence. But still, this formula again was obtained with a simplification. So it means that if you go, will go to gross marks, for example, I would recommend you to go. And while deriving this formula, it was used approximations that we consider only, we introduce some delta function at Fermi energy, and we consider only electrons at Fermi energy, which works very good for low temperature and doesn't work for higher temperatures. Therefore, there is, if you will do mathematics correct, without this approximation, there will be a small dependence on temperature. But even in this case, it will be weak. Therefore, physically, it's very important for us to understand that really a susceptibility of paramagnets when they are metals behaves differently if they are isolators. They really, it's weakly dependent on temperature. That's first. And second, it's in principle smaller, significantly smaller than susceptibility for isolators. Because as we know, only some electrons occupying place close to Fermi energy is taking part in all this process. We did not discuss completely here diamagnetism of Landau. So there is Landau model where he has shown that in metals, diamagnets, their susceptibility will be 1/3 of Pauli susceptibility. But that's already a bit in depth, but just keep in mind that there is another model of Landau how to describe diamagnets in metals and conductors. And for us, yeah, so this important just to keep in mind that really temperature dependence is weaker. And Stoner model of ferromagnetism. What we do, now we are merging Pauli paramagnetism with Weiss theory of ferromagnetism. And idea is very simple. The same two parabolas for spin up and for spin down. And now, but we have now this QM. You remember internal magnetic field that we know that within this Q is an exchange interaction. So exchange interaction is responsible for this internal molecular field. But what it does in the system, this internal magnetic field, in fact, it takes part of electron from this region, right here, and moves them up. So that's what internal field is doing, and when this happens, it decreases energy. So that's what this internal field wants to do. It wants all of our electrons to point in the same direction, yeah? But it cannot. Only part of them can be shifted up. And why it's important? Because when internal molecular field, let's say, or exchange interaction, did this one, it decreased potential energy. So the system is more favorable in terms of potential energy, which wants minimum when all are parallel. But on this axis is kinetic energy of electrons. Yeah, and it means that if I take electron from here and put it higher, I increase kinetic energy of electron. So it means that we are decreasing potential, but we are increasing the kinetic energy. Therefore, what is important for us here is to take into account both contribution, in change in kinetic energy and change in the potential energy. And because any physical system will try to minimize the total. So change in kinetic energy is easy to calculate. What you need to do, it's more or less you need more or less to calculate total energy of all these electrons, and then you have the width, let's say, of this shape will be G as the Fermi energy times delta E, and the width of this, height of this region will be delta E. Therefore, you will get here delta E, because number of your electrons is this one, G E Fermi delta E over 2. This is the number of electrons which we moved here. And okay, and then we increase energy of each of them by delta E. That's why delta E is appearing here. So this is increasing the potential energy. And you see it's in kinetic energy, and it's with sign plus. But we will have also decrease in potential energy, so it's staying here with minus. And this one can be calculated the following way. So here is magnetization, which you can simply find again the difference in number of electrons at this level and up the number of electron, density of electron with spin up minus density of electron spin down. Each of them carries magnetron Bohr, and then having simply this number, you can come to this formula. That magnetization is again proportional to the delta G, like it was in the susceptibility in Pauli paramagnetism. It's proportional to the density of states at the Fermi level. And having this this formula, this is potential energy of magnetic moment placed in magnetic field B. You can immediately derive the change in potential energy through internal field Q, Weiss field, with taking into account directly this magnetization. But m squared, because internal field is proportional to m as it was proposed by the Weiss. Therefore, we can derive this formula for the potential energy, which is staying here. But for us, it's important, it's also proportional to delta E squared, but important that it stays minus, and here staying Q, internal field or exchange energy. So it means that if there is no exchange energy, then this term is equal to 0, and this motion of electrons up would be energetically unfavorable. You just increase system. But if you have large enough interaction Q, then this total difference can be negative. So it means that you can decrease energy if you will move electrons up. And this brings us actually to the Stoner criterion of ferromagnetism. Yeah, so all this is named Stoner model for ferromagnetism. The Stoner criterion says very simple that if you want your system to take place, that it really exists, stable, you need this delta E will be negative. So it means that your system, because of exchange interaction, decreases energy, total energy of the system. And if you will take the simple formula, we'll put it smaller than 0, you will come to the Stoner criterion, which shows that this product, where you see Q, magneton Bohr square, density of electron Fermi, should be larger than 1. Or you can rewrite it through atomic exchange integral. That's something very similar to Heisenberg integral J, but it's staying here, and it's rewritten in such form. But the idea is that this is exchange integral, how strong exchange interaction is your media, and this is density of electrons at the Fermi level, and it should be more than 1. And now we are ready to answer the question why iron, cobalt, and nickel show spontaneous magnetization at room temperature. Why they are magnets? Here you see energy, exchange energy, U, in some arbitrary units, as a function of atom numbers, atomic numbers. So it means we discuss here, we show different materials: lithium, sodium, scandium, iron, cobalt, nickel, rubidium, palladium. And you see that exchange integral for lithium actually is much larger than exchange integral for cobalt, nickel, iron, or for sodium. So these materials want to be more magnetic than that magnets which we know. At the same time, if you will plot density of electrons, this is G function, G as density of electrons then, at the Fermi level. It's not, so somewhere hidden here. Then we will have here, this is G as a function of this, that. You will see that for sodium and for lithium and so on, for all other materials, density is very small. So there are not enough electrons having energy of Fermi energy. Therefore, when we will multiply U with G, you will see that this product is below 1, like it's shown here. Therefore, they are not magnetic. They don't show spontaneous magnetization. If you will go to very high, heavier materials like palladium, you see that it has quite good density of state, but low energetical level and low exchange interaction. Therefore, when you will multiply one with another, you again will stay below 1, below this level. And only 3 materials, iron, cobalt, and nickel, have large enough density of state and large enough exchange interaction that when you multiply it, you can satisfy Stoner criterion, and these 3 guys are magnetic. They show spontaneous magnetization at room temperature, so their susceptibility can be larger than 1. Yeah, and then susceptibility is very similar to the Pauli susceptibility, but again, you need to take into account this factor, which more or less exchange interaction or internal field of Weiss. So that's the same like we have seen, but here we have, you see, we don't have any more number of electrons. We don't have here yet total angular momentum like we had it earlier in Brillouin function. Instead, we have density of state at Fermi energy because we use completely different model. I want to discuss this one. So here I introduce little correction. Pauli susceptibility. So this high, it's not really a susceptibility of ferromagnet, which, as we know, can be larger than 1. It's a paramagnetic susceptibility with taking into account of additional term coming from a Stoner criterion. Why it's important? Because this Stoner criterion, we need this term to be larger than 1, and in this case, as a system will show spontaneous magnetization, so it will become magnetic, like for this cobalt and nickel iron. And what's important is that if you will have this term larger, then if you will simply plug it into the formula, you will immediately get negative susceptibility. First of all, it will go to infinity when they're equal, and afterwards it will become negative. And these both cases are unphysical. So we don't really have here, so we cannot use this formula for ferromagnets. It's only susceptibility of paramagnets with taking into account exchange interaction. So we need to work only for the cases when this part is smaller, so than 1. It's still final lecture, but we already making a step. It's still basics lecture, but we are making a step towards magnonics with materials. There are many materials which are used in magnonics, and here is the list of some commonly used. So it's in this review paper we made some time ago. And here you see yttrium iron garnet, yttrium 3 iron 5 oxygen 12. It's a ferromagnet, it's a garnet, a very complicated structure, isolator. Ferromagnet means antiferromagnet with uncompensated sublattices. And here we split it into 2 types because it happened historically that first people worked with a micrometer thick YIG, and over the last years we learned how to grow. People learned how to grow very thin nanometer thick YIG and stain here. And then we have permalloy, which is nickel 81 iron 19. It's a metal. It's an alloy of 2 metals, very commonly used. Permalloy was developed originally as a material with smallest magnetostriction, which is used in transformators and other materials. There is cobalt iron boron, cobalt 40 iron 40 boron 20. And there are many other materials, for example, Heusler compound. It's a half metal, very complicated with very different structures, but also very attractive for spintronics and for magnonics. Besides materials which I know, some people use just high quality single crystal iron. It's very good material because it has small damping, and any other material which has small enough damping can be used. Which parameters are important for us? First of all, of course, chemical composition. Gilbert damping parameter, we will discuss alpha. Shows how large damping is, and you see 10 to the power minus 5. It means that in YIG, it's 100 times better than in permalloy, approximately. Magnetization, so how large is magnetic moment? And YIG is ferromagnet, so it means uncompensated spin, so only one of magnetic moments of one ion is taken into account. Therefore, YIG has small magnetization, metals have larger, more than 1000 kilaampere per meter. Exchange constant, how strong there is interaction, and you see that it's not a big difference, but for metals it's a bit larger. Curie temperature, so above this temperature materials are not magnetic anymore, like it's shown here. And thicknesses with which people work, principally only for thick YIG, there is some limitation technological how to grow it on gallium gadolinium garnet, but usually it goes from atomic layers up to any thickness you want, but this is the commonly used I don't know, from 5 to 100 nanometers. That's what we use for magnonics. Lifetime, very important. It depends on frequency and on ellipticity of precession and so on. Here in this table is just a value for you to get a feeling how long magnons live. So in thick YIG they will live several hundreds nanoseconds. In metal they will live several nanoseconds. Velocity, how fast our spin waves, again, it strongly depends on the K, on the frequency, if this is a magnetostatic or dipolar magnon, or this is an exchange magnon. And then it can be tens of kilometers per second, it can be few kilometers per second. Principally, magnons can be also much faster. Still, they are much slower than photons. So we need to keep in mind that spin waves are slower than light. And how long distance spin wave can run? Centimeters in SIG-YIG, microns, tens of microns in nanostructures. Yeah, and also sometimes for data processing, it's important to normalize your free path by the number of wavelengths to know how you can, how good it is for data processing. And you see that in SIG-YIG it can run 40 wavelengths. In metals, it runs only several wavelengths. But if you will use, for example, a YIG and will go to exchange waves, and prediction says that you should have many hundreds of wavelengths when spin wave propagates. This is shown only for MSSM, magnetostatic surface spin waves, which we'll discuss soon. So this is a general overview. The summary would be that any material in which Gilbert damping is good enough is suitable for magnonics. And with this, we are done with fundamentals of magnetism.